Hey guys, we're going to go over optical techniques today and the role that optical techniques play within the clinical chemistry laboratory. So real quick, an overview. What are optical techniques? They're just basically any analytic technique that measures light absorption by a sample at specific wavelengths, or in human words, how much light does the specimen suck up? And this principle is the foundation of clinical chemistry analysis. Basically, any sort of analysis that you can perform within the laboratory, particularly ones that use analyzers, are going to be based on some sort of optical technique. And the reason for this is because we are going out of our way to use absorbance, so how much light the sample sucks up, to determine the concentration of the specimen. And we can do this by measuring absorbance at different wavelengths. We can measure like a lot of different stuff. And what this can tell us is concentration of the specimen, but it can also give us detailed information about the molecular structure of whatever it is that we're measuring. So before we get into spectrophotometers, we actually have to start with the basics of light. I'm sorry, this is painful if you don't like physics. Unfortunately, you kind of have to understand what's going on in order to get through it. I'm so sorry. Deal with it. Anyway, so when we're talking about the basics of light, the first three things that you need to know is that we are worried about the relationship between frequency, wavelength, and energy. How do these three things play together, right? Frequency and wavelength are things that we can use to describe the physical characteristics of light, and energy is what light is. Light is a form of energy. So how do the physical characteristics of light play into the energy that that light is displaying? The way that we talk about wavelength is physically, light is traveling in a wave. How wide is the wave? Okay, how long are the waves? Wavelength also refers to what color the light is. So depending on the wavelength that you are displaying, that changes the color of the light. Cool? Cool. Frequency is how many of those waves can we fit into a set space. So if I have a longer wavelength, I'm not going to be able to fit as many waves into the same space that I would be able to fit something that is shorter, right? So what we say in human, well, not human terms, the math terms that we use to describe that is that frequency is inversely proportional to wavelength. So as frequency increases, wavelength, or lambda is the thing that we use to refer to that, lambda decreases. As frequency decreases, lambda, or wavelength, increases. Cool? Cool. We have a formula that we can use to display the relationship between frequency and wavelength, and it is V equals C over lambda. So frequency equals speed of light, which is constant, over lambda, which is wavelength. Here is the number for speed of light. It's constant, it doesn't change. This is a universal principle within our universe, and it's wonderful. Cool, moving on. What is the relationship between frequency and energy? Because you remember, we said that we wanted the relationship between frequency, wavelength, and energy. We've already talked about the relationship between those two. What's the relationship between these two? Energy equals something called Planck's constant times frequency. Again, this is a constant. You don't have to worry about it. Energy is how much energy do we have in the system. Frequency is how many waves do we have in the system. The more energy that you have, the more frequency, the higher the frequency, I should say, not the more, because it's not a greater thing, it's an elevated thing. They are directly proportional. So as energy increases, so does frequency. As energy decreases, so does frequency. They are directly related, which leads us into what is the relationship between wavelength and energy? How do we discuss? Why is my phone ringing? What is the relationship between these two things? Well, as we said earlier, frequency is inversely proportional to wavelength, but it is directly proportional to energy. We have two formulas that we have already been over, so we can take this formula here, what frequency equals, and we can plug this value into the formula for energy as it relates to wavelength, or sorry, as it relates to frequency. And this is how we can get to the relationship between frequency or wavelength, wavelength and energy. We take this whole chunk and we plug it into the V right there. We take that chunk and we plug it into frequency. My phone keeps ringing, I'm sorry. Anyway, so when we do that, we end up with energy equals H, which was Planck's constant, as we learned a second ago, which, by the way, that's that number. I would know that number. We had to know that number. I would know that number. We take energy and we multiply, or energy equals Planck's constant times speed of light over wavelength. If you're like me and you need to simplify things down because you need things to look nice, you can simplify it and you can multiply H by C, and you end up with energy equals Planck's constant times the speed of light over lambda. It's really that simple, which means that because the relationship between frequency and energy is direct, and the relationship between frequency and wavelength is inverse, then that means the relationship between these two things is probably inverse as well. So what ends up happening is as frequency increases, wavelength decreases and energy increases. As frequency decreases, wavelength increases and energy decreases, because energy is inversely proportional to wavelength. This is known as Planck's law, which is the relationship between wavelength, or the color of the light, and energy. We've made it through the painful part. We're good. Good job, everyone. You have survived. Congratulations. Let's talk about what spectrophotometry is. Also, oh my goodness, can you? Sorry. So, let's talk about spectrophotometry. What is spectrophotometry? Well, like I said a minute ago, it's an optical principle. It's an optical technique. Optical techniques use light to determine concentration. In this case, spectrophotometry checks to see how much light is absorbed by a substance, and it uses that absorption to determine the concentration. The components of a spectrophotometer include a light source, right? We need light in the system. We're using light for our measurement. You have to have light there. You have two options. You can either use visible light, so the thing that your eyeballs can physically see, or you can use UV light. If you're using a visible light, you use a tungsten lamp. If you're using UV light, you use a deuterium lamp. Straightforward. We also need to have something called a monochromator. The monochromator is the Pink Floyd of this system, if that makes sense. So it is either going to be a prism or a grating that takes that light source that we're working with and splits it so that we can isolate the specific wavelength that we want to test. Like you've seen in chemistry, you know how different reagents, like she'll give you like, this reagent absorbs best at this wavelength, and she'll be like, at 540 nanometers, that's what you use for this reagent, right? That's because we are literally going in and selecting the wavelength that we want to blast the sample with, and we do that with a monochromator. We take the light and we break it up into all of those different bits, and then we say, I want that one. And then we filter the light so that only that one gets through. And then it passes through, and then we push it to the sample, and it hits the sample. Yay! That's what a monochromator does, okay? We also have to have something called a sample cell, which is just what it sounds like. It's the thing that your patient's specimen goes inside of. This can also be called a cuvette or a reaction vessel. I will say, in my experience, I have usually heard them referred to as RVs. Different labs do different things. This is just my own personal experience. I usually hear RVs. It's beautiful, right? Last thing that we need is a photodetector. So it's all well and good that we're blasting light on the specimen, but we need something to do the measurement. Otherwise, we're wasting our time because we're not measuring the thing that we're trying to measure, right? So what we use for a detector is a photodetector or a photocell. What this does is it's like, hey, how much light has hit me? Cool, thank you. Let me tell the computer. And it takes the amount of light and it converts it into an electrical charge, pushes the electrical charge to the computer. That way the computer can be like, ah, yes, I understand what's going on here. I see how much has been passed to me. I know how to do this. Cool? We have 3 types of photodetectors. You have a photocell, which is the cheapest one. Most of us like this one. It's basically you have 2 layers. You have the layer that the electrons or that the light physically hits, and then you have a silver layer. And then as the light hits this layer, it knocks electrons off of the light sensitive layer, and those electrons cross over and hit the silver layer. And when they hit the silver layer, it generates an electrical charge that is then passed to the computer. These are great because even though they're made of silver, they're very inexpensive because it's not a lot of silver, it's a very thin layer. It's wonderful. They're also very durable. They can take a lot of hits, they can last a long time. They're great. The other option that we have is a photomultiplier tube. A photomultiplier tube is who's the guy that went up? Is it Paul Revere? The guy who was like, the British are coming, and he was going around the whole town yelling about it and just amplifying their presence, making it known that there were the British that were coming. Photomultiplier tube works in the same way. It sees light, it yells light. It sees light, it says, guys, there's light here. Make more light. And it makes more light, and it increases and multiplies the amount of light present within the system in order for the computer to be able to interpret what's going on. This is great. It's sensitive, very sensitive. This is the thing that we like for tests that need sensitivity because they have a very, very, very low amount. We love photomultiplier tubes. We use them in 2 very specific things that we'll get to later. It also can last a long time. It doesn't it's not prone to exhaustion the way that a photocell might be or a silicon photodiode might be, right? Because if you have a bunch of stuff hitting this, the silver layer needs time to recover the electrons in order to keep going. So the photomultiplier tubes are great because they're not sensitive or they're not prone to fatigue, if that makes sense. Silicon photodiodes, all that you need to know here is that light strikes the diode junction. That's it. I'm so sorry. The other thing to keep in mind, the anode must be positive compared to the cathode. Just memorize that. I'm so sorry. It's just something that there's not much application for that knowledge, so it's not really worth going out of your way to understand it. Factors to consider when you're running a spectrophotometer. What range can your spectrophotometer analyzer measure? So what wavelength range, what range of wavelengths is your analyzer detector physically capable of detecting? The other thing that you need to worry about is what wavelengths can the light source produce? So say you have a tungsten lamp and your tungsten lamp is producing visible light. What range of visible light is your tungsten lamp producing? Is it producing from, 465 nanometers up to 555? Is it producing from 460 nanometers all the way up to 630? Is it what amount of visible light that we can see is this tungsten lamp able to produce versus, if it's a deuterium lamp, it's the same thing. What range of UV light can your deuterium lamp show? The other thing is the source of radiant energy. What type of light is being used? So again, that goes into the deuterium versus tungsten, but it's more so if I need to measure something visibly, if I need to measure something with a visible wavelength of light, I wouldn't want to use a deuterium lamp because a deuterium lamp is UV generation. If I need to measure something with UV light, I wouldn't want to use a tungsten lamp because a tungsten lamp is visible light generation, if that makes sense. So it's not just that you need to be using the right type of light, it's the range of light that bulb can produce within that type of light. Those are 2 things that are important here. The other thing to keep in mind is the stability of your radiant energy over time. So when we first validate our instruments, we're using fresh light bulbs, right? We're using fresh bulbs, we're using fresh systems, where everything is great. But what happens as the light starts to die? What happens as we go through all of this and it's been a year and the light is not as strong as it used to be? Well, the computer doesn't have a way of knowing that there's less light coming through the system. It thinks that the light was fine. That's a problem, and we'll get more into why later, but you just need to know for right now, stability of radiant energy over time, you need to make sure that, when the bulb is new versus when the bulb is about to die, that they're still pretty comparative to each other. Other things that we need to be concerned about is temperature. Heat is energy, and like I said earlier, we're measuring the relationship between energy, frequency, and wavelength. This is assuming that the system within the analyzer is a closed system, which means that there are no other forms of energy getting in the way and causing a problem. Temperature is energy, heat is energy. The more heat that you have in your system, the more potential you have for heat to come in and punch its way into that reaction system and cause a problem. This is an invader, and it likes to get in the way of things. There is a reason why laboratories have to be kept cold, and it's because the analyzers are instruments, and computers get hot when you use them. So you will have like refrigeration systems that go crazy within these analyzers, just specifically trying to keep, at the very least, the reaction chamber at a realistic normal temperature to prevent the interference of heat from getting in the way and messing with our closed system up here. Other things that you need to be aware of is your cuvette shape. We have two types mainly. You can have a rounded cuvette and you can have a square cuvette. If you remember from physics, like the concept of lenses bending light, a curved cuvette, a curved reaction vessel, can also refract light in that same way. And if our whole goal is to see how much light makes it through the sample and gets to that photodetector, anything that's refracting light off is going to be a problem because it's going to falsely lower the amount that makes it through to the end to the detector. That's a problem. We don't want that. That causes more error because it warps the light. On the other hand, we have square ones, which are ideal because they have flat sides, so they don't really have that same issue with refraction error. We can also worry about the type of material that the cuvette is made out of. It could be made out of quartz, it could be made out of glass. Glass is less expensive, so there are real benefits to using glass, but it absorbs UV light. So if you are working with a deuterium lamp, for example, which makes UV light, you may not want to use a glass cuvette because that's going to start to get in the way and it's going to be, you're going to have it absorbing into the glass or into the quartz itself or into the glass itself. Yeah, into the glass itself. And it's not going to be making it into the specimen. And the rule that I need you guys to understand is that computers are stupid. Computers are so stupid. They only know what you tell them. Okay. And so if I have light getting absorbed by my glass, and I have light getting absorbed by my specimen, the computer thinks that all of that light is being absorbed by that specimen because we haven't told it that light is going to be absorbed by the glass. All that it knows is that all of a sudden there's less light making it through to the end of the system, which means that more of it got absorbed, but it assumes that all of that increased absorption occurred within the sample. That's a problem. We don't like that, okay? On the other hand, when we start talking about UV light and like absorption of UV light, we can use quartz cuvettes. Quartz cuvettes are great because they don't absorb UV. They are expensive. So if you're measuring something that's like within your visible light spectrum, it's not really worthwhile to do quartz because it's expensive. We also, when we're talking about spectrophotometry, we have to worry about QA in a couple of aspects. So one of the biggest things that we have to worry about is wavelength calibration. This is basically our way of making sure that the wavelength that we have selected is correct. Are we hitting it with the right wavelength? Have we chosen the right nanometer for this specific specimen? We need to make sure that the monochromator is splitting light correctly. We need to make sure that the monochromator is not accidentally angling all of the light that has been split. And we also need to make sure that the filter that we're using to just like select this specific wavelength of light is seated appropriately. Well, we have a couple of different calibrators that we can use to determine that. We can use didymium or holmium oxide. These are just reagents that we can use to like go through the process of determining that these things are functioning. The other thing that we have to worry about in QA is that our instrument displays a linear relationship between absorbance and concentration. And so the way that we do that is we make a concentration gradient. We make a bunch of different samples, I guess. We make a bunch of precisely prepared dilutions, and then we measure the absorbance of all of those to make sure that, yeah, that's a linear relationship going on. Okay, so I'm gonna take a drink real quick. I'm thirsty. I've been talking for 20 minutes straight. Anyway, now, Again, like I said a second ago, the rule that I need you to understand is that computers are stupid. The second rule, light loves to play tricks on everyone, including computers. Light is mean, light is a bully, and computers are stupid. So, when we're talking about light playing tricks on us, we have to know what incident light is. So, when I have my spectrophotometer, I have my light source, right? It's beautiful. Light source. I should be an artist. The light source is shining light onto my sample. All of the light that is shining from the light source onto my sample is referred to as incident light. Now, incident light is the light shining on the sample prior to hitting the specimen. This is the baseline for measurements. So this is our like foothold, I guess. It's like when you're like taking a weight of something and you zero out the scale beforehand. This is our point of reference for how much light should be like in the system in total. We need to very precisely make sure that the amount of light that it, or the amount of incident light, like we need to know what that is. The more that we can guarantee that our incident light is what we say it is, the more that we can trust the results that we get based off of calculations that we do from incident light, if that makes sense. So the more that we can guarantee our incident light, the more that we can guarantee our results, which means we really want to avoid any kind of problems that could be impacting something that would change like how much we can trust our incident light value. How much do we, like, we need to, and I cannot harp on this enough, you need to know exactly how much light you are putting into your system in order to know how much light you should be getting out of your system. So if I have like an environmental light contamination, so say I'm working on my analyzer and I open up my reaction chamber as I'm running my reaction, and all of a sudden I've introduced like 30 or 40 times more light than I initially had within my specimen reaction chamber, not reaction vessel, reaction chamber. Reaction chamber is where this all occurs. If I suddenly introduce a bunch more light, the computer is stupid and the computer doesn't know that that light is not supposed to be there. Why am I? Thank you. Okay, that's just, we're just gonna go with it. Anyway, computer is stupid. The computer doesn't know that I've just multiplied the amount of light that I have within my system by a factor of 30 or 40. All that it knows is more light. More light means more concentration. That's not good. We don't want that. The other thing that we have an issue with is if the light source that we're using is bad. So if our light is starting to die, or maybe one of the filaments within it is sort of like futzing around and like sparking, that's a problem. Because again, it makes it so that you can't trust your incident light measurement. The other thing is a bad sensor. So all of this light passes through your reaction, through your specimen, and it hits your sensor, your photodetector at the end. If your photodetector stinks, then you're not going to be measuring what's coming out of your system, right? Like you can know all you want about what's going into your system, but if your photodetector sucks, you're not going to know what's coming out of your system. So now we know what incident light is. Incident light can be broken up into what is absorbed by the specimen, what is transmitted through the specimen, and what is reflected by the specimen / the reaction vessel. So what's absorbed? That energy goes into the solution and dissipates within your specimen. The more your concentration, the more gets absorbed. What is reflected? It goes, the light, the energy, everything goes and hits the sample and goes. Doesn't do that. It goes, boom, bye, not my problem. What's transmitted is the stuff, the light, the energy that manages to make it all the way through the specimen and keeps going because nothing stopped it. It's like, did y'all ever do the buckle challenge in high school when you went to like the buckle store and you would like go into the store and try to get all the way to the back wall to touch the back wall without an employee stopping you to say hello? That's like such a niche reference, but you can think of transmitted light as the buckle challenge, trying to get to the back of the buckle store before an employee stopped you to say hi. The more employees that were there, the higher the concentration of the analyte. The more employees that were there, the harder it was to make it to the back of the store and touch the back wall and win the challenge, right? Transmitted light wins the challenge in this instance. So What is the difference between transmitted light and transmittance? Well, transmitted light is the raw measurement. So that is the raw number that the photocell comes up with. Transmittance, on the other hand, is a comparison of that transmitted light to incident light. So your transmitted light can also be referred to as I1, and your incident light can also, well, I guess it's L, but whatever, I naught. Okay, so you have I naught, I1. So if we're talking about transmittance, transmittance would be your transmitted light over your incident light. Because incident should be our like total amount of light that we expect to see within the system, and then transmitted is whatever fraction made it through. We can also talk about transmittance in the context of percent transmittance. So percent transmittance is literally just transmittance times 100 so that I could display it as a percent. That's quite literally the only difference that's going on there. Transmittance, like without the percent, is really helpful for most mathematical calculations with the exception of the one formula that you need to know. Whereas percent transmittance is usually not great for math, but is ideal for talking about. So it's ideal for being like, hey, I had 75% transmittance, as opposed to, hey, I had 0.5 or 0.75% transmittance. Like 75% just makes more sense to most people's brains, so we use it more for talking. Transmittance is on a ratio, and it is going to be expressed as a number between 0 and 1. Your transmittance should never be greater than 1. Okay? Because transmitted light, because I naught equal, or because incident light equals your absorbed light plus your transmitted light plus your reflected light, and your I naught is like your like 100%, your like whole percent. Transmitted light should never be greater than the amount of light that you're physically putting into the system, right? Like transmitted light should only be a portion of that total light. Transmitted light, if you have a number of transmittance that is greater than 1, that implies that your transmittance is greater than I naught, because that's how ratios work, right? Oh my goodness, can I help you? Okay, it's fine. Transmitted light is greater than, if your transmitted light is greater than your I naught, shouldn't be happening. That's how you would get a number greater than 1 or a percentage greater than 100%. Shouldn't happen. If you get that, check yourself, because that's wrong, and that's a problem. Total light, again, is made up of absorbed, transmitted, and reflected light. Total light is our like complete or total. So it's our like 100%. It's our frame of reference, our benchmark. As transmittance goes down, absorbance should go up, because these are inversely proportional. So as one goes up, the other goes down. As one goes down, the other goes up. We have a formula that we can use to relate transmittance and absorbance. They are not exactly linearly related. They are logarithmically related. But our formula for the relationship between absorbance and transmittance is A equals 2 minus log base 10 of percent T. So you remember how a second ago I said that literally everything else uses not percent T, you just use T. Because this is the one singular formula that uses percent T, it also happens to be the one formula related to like this direct relationship that you need to know. It's the whole thing. We use percent T with this one, and it's a real thorn in my side. Anyway, if your transmittance, so if the fraction of light that transmits all the way through your specimen is equal to 100% or 1, then that implies that 100% of your light transmitted through the specimen, which implies, on the flip side, that 0% or 0 of your light was absorbed, because those two things are opposite. So if you have 100% transmittance, you have no absorbance. Let's do some math real quick. So if T equals 0, oh my gosh, come on. If t equals 0.387, what is percent t? Well, remember a second ago I said that percent t is just t times 100? So that would be that times 100, which equals 38.7%. All right, next question. If percent t equals 43.5, what is absorbance? Well, we have our formula up in the right-hand corner, but let's go ahead and just rewrite it down here because I'm anal retentive about stuff like this. A equals 2 minus log of percent t. Okay, which means this is going to be 2 minus log of 43.5, which means calculator log base 10 of 43.5, and that's going to be roughly 2 minus 1.64, roughly, which is going to then be 0.36 equals your absorbance. If t, let's take this a step further. If t equals 0.649, what is absorbance? Well, our formula says A equals 2 minus log percent t. Well, percent t and t are not the same thing, okay? Our formula for percent t is t times 100. So we can just take this and plug it in there. So we will get A equals 2 minus log of t times 100. Does that make sense? So then in this case, that's going to be 2 minus log of 0.649 times 100, which is going to equal log 9. That's not the right number, 64.9. There we go. Come on. Which equals 2 minus 1.81, which is going to roughly equal 2 minus 1.81 is going to roughly be 0.19 equals absorbance, where absorbance is just how much light was sucked up by the sample. What fraction of light was sucked up by the sample? So a few rules. First rule is that concentration is directly proportional to absorbance. So as concentration goes up, absorbance goes up. Concentration is inversely proportional to transmittance. So as transmittance goes down, concentration goes up. Couple other rules I'm just going to throw out there again for the sake of driving it home. Light plays tricks on us and computers are stupid. That's not important here. It is important to know in terms of chemistry. Computers are stupid. I love computers. Computers are very stupid. Anyways, all of that in mind, we found our absorbance. That's great. How does absorbance actually relate to concentration? Because I mean, it's all well and good to sit here and talk about proportional versus direct, like inversely versus directly proportional and how like all of that is, but how do we calculate it? Well, we can use Beer-Lambert's law, okay? This is how absorbance gives us concentration. The thing about Beer-Lambert's law that we really like is that it does accommodate specimen variations, right? So the thing about Beer-Lambert's law is it can tell you, it can accommodate like how well your specimen is mixed. Is your tube crusty dusty? Are we losing scattered light? Stuff like that. So Beer-Lambert's law is nice. It just has some accommodation going on there. Anyway, our formula for Beer-Lambert's law is absorbance equals something called molar absorptivity times path length times concentration. Take a moment, pause. We've seen the letter C used in two different formulas so far. Just know that little c and big C are two different things. Little c is the speed of light and it's a constant. Concentration is what we want to know about our sample, right? Those are two different things. So just keep in mind, different C, different outcome. So absorbance, again, how much light was absorbed by the specimen. Molar absorptivity is how much a substance likes to suck up that light. Like how much does this thing like to go suntanning on the beach? How much does it love light? Especially at that specific wavelength, because again, as per usual, we're using that monochromator and we're splitting the light up and then we're filtering out which wavelength we want. How much does it like to suck up the specific wavelength that gets through the filter and after it goes through the monochromator? Path length is the distance that the light travels through the sample. So it is usually 1 centimeter. For our purposes, it's usually 1 centimeter. And that is in part because it's small, which means that we only have to run a small amount of sample, but also because it makes the math significantly easier that it's 1 centimeter. It means that you don't have to worry about some stuff with math. It's wonderful. We love it when it's 1 centimeter. Lastly, concentration. This should be a capital C. I know that I said small c, should be a big C. Concentration is just how much stuff is in your sample, okay? So let's go ahead and do a really quick version of this. So the absorbance of a solution is 0.757. Epsilon, or molar absorptivity, is 6.22 times 10 to the third liters per mole centimeter. This is like constant for each specimen, or like constant for each analyte, but it'll ignore that. Ignore what I just said. Anyway, path length is 1 centimeter. What is the solution's concentration? Well, we can look at our formula real quick, which is going to be absorbance equals epsilon, or molar absorptivity, times path length times concentration. We have absorbance, we have molar absorptivity, we have path length, we need concentration. So we need to isolate concentration. We do that by dividing both sides by molar absorptivity times path length, which leaves you with absorptivity over that equals, you can cross those two out, equals concentration, okay? So then we're just gonna move over here, A over molar absorptivity equals C. And then we can plug and chug. So A is 0.757 over 6.22 times 10 to the third times 1. Do you see why I said it makes the math easy? It makes the math so much easier. So then we would just divide 0.757 by 6.22 times 10 to the third, and you are left with our concentration equals 1.22 times 10 to the fourth moles per liter. That's how you would get to that point, okay? So what happens if we don't have molar absorptivity, right? Like what happens if I don't have this? If I don't know how much something likes to suck up light? Like what if I don't know that? Sometimes it happens. Sometimes it's really annoying. Life isn't perfect. Well, luckily, I can't talk all of a sudden. Luckily, a bunch of lovely scientists have gone out of their way to establish standard curves for a lot of the analytes that we are measuring, and specific labs will also do their own standard curves for their own analytes that they're measuring. Basically, a standard curve is just a linear display, or a display of the linear relationship between the concentration of an analyte and the amount of light that it's absorbing. Wonderful, right? So we already know, for the most part, what dye correlates with what wavelength. You guys have already learned several of them. So like, for example, what's the wavelength for albumin? What's the wavelength for bromocresol purple? Stuff like that. Like, you already know this because scientists have already found them. They went out of their way, they measured absorbances of a bunch of known standards, a bunch of known concentrations, plotted them, got the slope, used the slope to determine what we would expect in order to find all of this stuff. Once we have that slope, we can then go and take our patient, put our patient sample on the spectrophotometer, get the absorbance, and then use the slope of that curve that we have established to calculate what we think is going on with that patient's sample. So if we don't have our molar absorptivity, it isn't a problem. You can use your standard curve. Now, do you remember from Gen Chem back in undergrad, the formula C1V1 equals C2V2? We have our own version of that, which is the concentration of an unknown over the absorbance of an unknown equals the concentration of the standard over the absorbance of the standard. This is just a ratio comparison. That's all it is. It's really simple math, I swear to God. It's so simple. We can also, if we're like, again, this is the thing that we're generally looking for, is the concentration of the unknown. So this just walks you through the process of how to get to the unknown concentration based on having these other three things. You would multiply both sides by the absorbance of your unknown. You can then simplify it by crossing out absorbance of the unknown over on the left-hand side to get you just isolate concentration of the unknown. Isolating concentration of the unknown, you're left with concentration of the standard over absorbance of your standard times absorbance of your unknown. And then you can again simplify that by multiplying absorbance of your unknown with by that fraction, which then leaves you with concentration of your unknown equals concentration of your standard times absorbance of your unknown over absorbance of your standard. Whew, that was a lot of words. Anyway, let's do it in practice because there is a difference between talking at you and working with you. So, at a standard concentration of 4.0 grams per deciliter, right? Standard concentration, CS, albumin's absorption is 0.21. So at the standard concentration, the standard absorption of albumin would be, standard absorption would be 0.251. Our specimen absorption for our patient, so our absorption of our unknown is 0.284. What is the concentration of this patient? Real quick, just a self-check moment before we get through the math. Our unknown patient's absorbance is slightly higher than our standard's absorbance, which means because absorbance and concentration are directly proportional, we can assume that because our unknown's absorbance is slightly higher than our standard's absorbance, that means that our unknown's concentration is probably going to be slightly higher than our standard's concentration. Does that make sense? Anyway, let's go ahead and fill out our formula. I forgot to put it on this slide, but it's Cu over Au equals Cs over As. Cool? Cool. Let's go ahead and we're going to isolate out our, what are we working with? We want our concentration of our unknown equals question mark. So we want to multiply both sides by Au, cross that out. So then we end up with Cu equals Cs Au over As. We can go ahead and plug and chug now. Cu, so then Cs is 4.0 times Au, which is 0.284, over As, which is 0.251. Which is going to be 4 times 0.284 divided by 0.251. That's going to equal roughly 4.53 moles. Sorry, not moles. It's going to be grams per deciliter equals our Cu. Now back to that self-check moment that I had us set up earlier. Our Cu is supposed to be slightly higher than our Cs. Our Cs is 4.0. 4.53 is greater than 4.0, which means our self-check is good. That way of quickly checking our math, we're okay. All right, now that we have survived spectrophotometry, let's go through a couple of other like miscellaneous methods that we can use when we are doing this kind of stuff in lab. So other than regular spectrophotometry, we also have something called reflectance spectrophotometry. Reflectance spectrophotometry is spectrophotometry with an extra step, okay? I'm gonna make myself smaller just because I'm looking at myself over here and I'm realizing I might be blocking some of the photos. So we're gonna make me a little bit smaller. Anyway, back to the PowerPoint. So reflectance spectrophotometry is basically the exact same thing as regular spectrophotometry. You have your light source, we didn't go over what a collimator is, don't worry about it, it's just a condenser, essentially. It just makes the light smaller to like focus it for the monochromator. Monochromator is there, splits the light. The light goes through our filter to select the wavelength, it goes through our sample and is absorbed by our sample, and then, oh, we're supposed to be hitting our photodetector, but we're hitting something else. I don't know what this is. We're gonna go in a different direction, okay? There's the detector. Isn't that beautiful? I wish there's one thing that I wish was different about this uh, graphic, and it's that you have the light passing through the sample 2 times on this graphic. I don't love that. The light should be passing through the sample 1 time on this graphic. It should be here, bouncing off, and like maybe not at a 90-degree angle, but like it shouldn't be passing back through. So the detector should realistically be like here. Unfortunately, this was the only half decent graphic that I could find for this concept. Anyway, what is this? What is this thing? Well, this thing is called a white optical diffuser. It's basically just a backboard for the light, and we let it go through, and we let it hit the backboard, and then from the backboard, it goes to the detector. We are measuring the amount of light that is reflected, but note that this light that's reflected is not the same as like the incident light earlier reflected light breakdown. It is not that reflected light, because that's the light that reflects off before we even hit our sample, right? We're not measuring this light. We're measuring the light that bounces off of the backboard, off of that white optical diffuser. It is important to know that the white optical diffuser is behind the sample. It is not the light that is lost before the sample. It's the light that's lost, is transmitted through, and then bounces off, okay? We are measuring that reflected light. We're measuring the like through reflection to find the concentration. The reflected light in this context, not this reflected light, this reflected light is inversely proportional to the concentration, because this reflected light is just the transmitted light. So you can think of it as if in this context, transmitted light and reflected light are the same thing, okay? The light that is transmitted all the way through reflects. And we're measuring the transmitted reflected light. Cool? Cool. Components, you use a tungsten halogen lamp for this, which means that we're using visible light for this. You will also use things that are called interference filters, which is basically just like anything that prevents extra wavelengths of light from getting in the way of what you're trying to measure. Again, you will use a white optical diffuser, which is this thing, the backboard. That's your backboard. That's not how to spell that word. This is the photodetector that uses the silicon diode. That's the one that we didn't go much into the principle of. Just memorize that reflectance spectrophotometry uses a silicon diode, okay? Examples of things that use this. Glucose point-of-care finger stick devices. So the things that people use to check their blood sugar with their fingers, that uses reflectance spectrophotometry. Urinalysis dipstick readers, when you guys get to body fluids, you will be using that. That's what that is. You'll see what they look like when you get there. That's all I can say. Otherwise, Orthodiagnostics Vitros chemistry analyzers. I've never seen one of those in my life. I don't know what they look like. Just memorize it. Otherwise, but the glucose point of care, urinalysis dipstick, basically anything that like is done at home, I would say you could probably get away with saying is a reflectance spectrophotometer. Take that with a grain of salt. Anyway, after we have talked about reflectance, let's talk about nephelometry. Nephelometry is scatter. So we're measuring how much light is scattered by the sample. I can't talk all of a sudden. So you have your light source. Your light source is shining on your sample. Your sample has a bunch of stuff in it. If y'all have ever played Plinko, you know the thing where you like drop the little token and it goes through like all of the nails and starts bouncing back and forth across in Plinko. Think of nephelometry like the Plinko of the clinical chemistry laboratory. The light goes in and it hits, and it goes in and it hits an analyte, and it goes in and it bounces off an analyte, and it goes in and it bounces off. The more particles that you have present in your solution, the more chances that you have for light to hit one of them and get bounced off in a different direction. Which means the higher your concentration, the higher your scatter. You will notice normally with our spectrophotometers, we have our light passing straight through and we have our photodetector over on the other side. You'll notice that with our nephelometer, our photodetector is actually off at an angle. And that's because the more light that hits it off at this angle, that implies the more light has been scattered by the solution, right? Nephelometry is really heavily dependent on particle size. The bigger the particle, the more likely it is to scatter stuff. Particle shape, abnormally shaped particles are going to be more likely to scatter stuff. particle concentration, the more particles you have in solution, the more chances you have to bump into stuff. And then incident light wavelength. So something that's got more momentum behind it is going to be harder to scatter than something with less momentum, if that makes sense. And like depending on the wavelength of light, depending on the speed that light, or not the speed, but depending on like how much force is going behind that light, it's going to change how much of it is physically capable of being scattered, because it might just punch through and not care, right? What is the difference between nephelometry and reflectance spectrophotometry? So like we said, the reflectance spectrophotometry is also taken at an angle, right? Reflectance is not based on scatter, though. It's based on a very precise redirection of light. So this, your collimator, right? Your collimator condenses your light down into a very specific size. It makes the light physically smaller. And then it goes through your monochromator and it splits it up into a bunch of different wavelengths of light. We pick the one wavelength of light that we want, and it stays very physically small the whole way through. It bounces off the backboard, and it still stays small as it keeps going through the system. The thing with nephelometry is that nephelometry is not keeping it very clean, right? Reflectance spectrophotometry, it's all that same single beam of light that's going through the specimen. With nephelometry, on the other hand, we are losing that beam. We don't care. The beam is gone. What happens instead is this whole thing should start to look like it's glowing, because it's going to send light into the system, and then light is going to come out at all directions. Okay? It's going to be lit up like a Christmas tree. Whereas this one over here, it's very neat, very organized, very demure, very mindful. Nephelometry, not demure, not mindful. Headache in terms of appearance. Interesting though. Fluorometry. So here's where it gets a little bit complicated again, and we have to talk back about the basics of light, and we'll get there in a second. So the principle of fluorometry is that molecules will absorb light at one wavelength, and then they will spit out that energy, because again, light is energy, so it absorbs the energy at one wavelength at a shorter, higher frequency, higher energy wavelength, and it'll spit it out at a longer, lower frequency, lower energy wavelength. Remember, wavelength and energy are inversely proportional. So let's talk through the physics of this real quick, right? When you have light coming in, light comes in, light strikes we call them what in the world? A chromophore. I can't speak. When light comes in and hits your chromophore or your fluorophore, that makes the energy of your photon go way, 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 way up. As your energy increases, your frequency of the light decreases, okay? When you give that energy a little bit of time to dissipate, right, that energy kind of starts to wane off, right? If you have something that's heat energy and you leave the hot object out, that energy dissipates and it gets cold, right? If you leave something that is glowing out and you don't reactivate it like a glow stick, you don't keep the chemical reaction going, the glow stick eventually will lose that light energy because it loses the ability to produce light, right? The same thing happens here. So we excite a particle. The particle starts to it hits a really, really, really high energy state, and then there's nothing keeping it in that high energy state. So the energy starts to wane and goes down, and it goes down. When we hit that excited state, you can't necessarily see it, but when we hit the emission state, that's when you can see it. We'll go through that fully in a second. Basically, what happens is we have a chromophore, and we hit it with a high energy wavelength of light. So we hit it high energy wavelength of light. The chromophore absorbs that high energy wavelength of light, and it sits with it, it holds space for the lyrics of Defying Gravity, and then a couple of seconds later, well, not necessarily a couple of seconds, after it loses a little bit of that energy, after that moment of like I've just been hit by something, calms down, after the energy dissipates a little bit, it then kind of is like, actually, I don't want this energy. This is bad. This is not for me. And it spits the energy back out. Because the energy has lost a little bit of its level, the energy spits out at a longer wavelength. Okay? That comes out. So this is in, this is what we hit it with, this is out, this is what it gives us back. Okay? Thing to note, looking up here in the upper right-hand corner, our shorter wavelengths, our UV light is a shorter wavelength, higher frequency, higher energy light than our visible wavelength. So in practice, if we are usually hitting our chromophores or fluorophores with a higher frequency, higher energy wavelength, we are usually hitting them with UV light. So UV light goes into our chromophore, and then what happens is sometimes we spit out visible light, which is lower energy, lower frequency. Does that make sense? It's like we hit it with high energy UV, it holds on to that, and then it decides, I don't want that actually, and it spits it out. The process of hitting the particle, hitting the chromophore with the light and pushing it up into that state of excitation is called excitation. I'm losing my train of thought. It's called excitation or absorption. So we are exciting the molecule, we are letting the molecule absorb the energy, and then when it spits it out, that is referred to as emission. We can visually see emission as fluorescence. It is glowing. That's what we're measuring. We measure the amount of fluorescence. We measure the amount of light that we're spitting out. So in fluorometry, we're not measuring the amount of light that we put in. We're measuring the amount of light that the chromophore spits back out. We measure. So the thing to note is that the more that we spit out, the more concentration, the higher the concentration there was for stuff to absorb stuff. So the higher the concentration, the more the sample absorbs, and then the more that it's able to kick back out for us to measure. So that means that fluorescence and concentration are directly proportional. Now, there are things that you have to keep in mind for those things to actually be directly proportional. First and foremost, the intensity of incident radiation. So how strong, how intense is the initial light that we put in to this situation? What is the length of the light path? So the longer the light path, the more chance that you have for that wavelength to like get longer and lose its frequency. Other things like molar absorptivity can impact this, and quantum efficiency can impact this. All that you really need to know there is just that there are things that can impact it, okay? We have some examples here. We have fluorescein isothiocyanate, which you will hear referred to as FITC, absorbs light. So it absorbs the wavelength 480 nanometers, and then it spits light back out at 530 nanometers. And I know for a second you're like, what? That's a greater wavelength. But remember, greater wavelength means lesser frequency, lesser frequency means lesser energy. So yeah, we're starting with a wavelength of 480, which is smaller wavelength, but that means that it's a greater frequency, greater energy, which makes sense because it absorbs at the higher energy level and it spits out at the higher wavelength, lesser frequency, lesser energy level. Okay? Sorry, I know that that's kind of a hard concept. Anyways, for our fluorometry, I can't talk anymore, man. I've been talking for an hour. For our fluorometry components, we have a light source, which is going to usually include a mercury or a xenon arc lamp. These can also be called your excitation source because these are the things that create the light that excites the molecules that causes the whole reaction to happen. You have two monochromators. You have an excitation filter. because we're worried about two separate wavelengths of light, we need to make sure that we are filtering for the correct wavelength that will excite things. So in the case of FTSE a second ago, we talked about it exciting at 480 nanometers. So this one, for example, might, filter for 480 nanometers, for example. And then it spits out at 530. So you want to have another filter that's going to filter for the wavelength that your sample is spitting out. So that might be, for example, 540 nanometers. Your excitation filter is going to filter what wavelength reaches your analyte, and your emission filter is going to filter what wavelength reaches your detector. We will use diffraction gratings for filters because gratings increase your wavelength selectivity. So it increases exactly how much or exactly how precise we are with our wavelengths that we're selecting for. Our cuvettes should be quartz. Glass absorbs UV. Glass also does this thing called quenching. So when we talk about, we're like measuring, the goal here is to measure the fluorescence that comes out of the specimen at the end of this whole thing, right? So we're putting light in and we're seeing what light this specimen produces because of the light that we put into it. Glass absorbs UV. So if we're putting UV light in initially and it's getting absorbed by that glass is now causing a problem because the glass in this instance is not going to fluoresce. It's just absorbing the light. And it's causing a really irritating problem because, again, computers are stupid. So if we have loss of light that is not caused by the specimen, it's caused by something else, the computer doesn't know that. It doesn't know that, and it causes problems because the computer is like, well, where'd all the light go? Well, it must have gone through the specimen. Lovely. Because we're measuring the amount of light produced, and the amount of light produced, the amount of fluorescence produced, this is opposite than spectrophotometry. The amount of light detected by your photodetector here is going to be directly proportional to your concentration. Whereas if it was like a spectrophotometer, the light detected is inversely proportional to your concentration. Because this one is a case where the light is directly proportional to your concentration, that's a problem if we're losing light because it makes it look like we have less light coming through, right? There's less light for the specimen to absorb because it's been absorbed by the glass, which means that there's fewer excitation moments within this specimen, which means that we are fluorescing less, which makes it look like our sample is lower than it actually is. It makes us look like we have less of our sample than we do. That's why we don't want glass in this instance. That's called quenching, is when you have that blocking from glass. Other things that can cause an issue, you can have like ethanol. Ethanol absorbs UV and can cause problems. So if you have an ethanol as a solvent within your solution, that can cause an issue. We use a different kind of detector for this one. We use the photomultiplier tube, which is the Paul Revere one that goes shouting that it found light, it found light, it found light, it found light, and it makes it everybody's problem. We use photomultipliers because photomultipliers have a higher sensitivity to lower light. Which means that fluorometry is going to be more sensitive than absorbance spectrophotometry. So the basic type that we learned about a minute ago, it's more sensitive than nephelometry. It's more sensitive than reflectance spectrophotometry, but it's less sensitive than chemiluminescence, which we'll get to in a second. The component or the advantages of fluorometry is that it's really, really, like, we have the ability to be very specific about our wavelength selection, and we can also be very, very sensitive with our measurements. Our measurements are very sensitive because we are measuring directly the emission of light coming from the excited particles on a zero-based background. So basically, we're looking for a single point of light in a field of darkness, which is going to be a lot easier than looking for a single point of light within a field of light, right? It's just, we're coming from a very dark background. It makes it a zero background. It makes it easier to see everything that's going on. So it's very sensitive, and we're photomultiplying what light is making it through, so it makes the whole thing very sensitive to stuff. Disadvantages: self-absorption. So we have talked about how all of these specimens absorb light at very specific wavelengths. But the thing is anything that has color is going to absorb light across the spectrum, right? It's just we are performing these tests at the wavelength that it absorbs light at the best, right? So it's not necessarily that this is the only wavelength where these things absorb light. It's just that this is the wavelength where it absorbs light the best. So that being said, if you have other light entering into your solution, sometimes that light can also get absorbed even if it's not the correct wavelength. Which means if our whole principle of this test is hit it with light, get it excited, make it produce more light, sometimes the new light that it produces can then go and hit other particles in solution and re-excite those other particles in a different manner, which is not what you want to have happen. So if you have a lot of self-absorption, which is what that's called, happening, that's a problem. You don't like that. The other thing, it is very sensitive to temperature changes and pH changes. So again, pH, temperature changes, you're talking about energy. If you start to have things interrupting a very highly sensitive method that's based on energy levels, it's highly sensitive. You have extra energy entering into the system. That's a problem because it's a sensitive little crybaby, right? We don't like that. Other disadvantages, you can have a very viscous test solution, which is just not fun. It causes problems. And then quenching, like I talked about a second ago, it's basically quenching is anything that reduces or inhibits fluorescence, which in our case, a lot of the time can be caused by using glass cuvettes instead of quartz cuvettes. But you can also have other reasons like photo bleaching, energy transfer, stray radicals, things like that. Basically anything that gets in the way of fluorescence is quenching. So chemiluminescence is kind of similar but different. So if the goal of fluorometry is to hit a particle with light, get it excited, and see what light it emits, chemiluminescence, on the other hand, is basically causing a chemical reaction and then measuring how much light that chemical reaction produces. So you basically mix your specimen and a luminescent reagent and you stick them together and it'll light up. And when it lights up, we measure how much it just lit up. As opposed to, I have one thing, I'm adding light into that system and I'm seeing how that light comes out of that system, if that makes sense. So with chemiluminescence, we're measuring the light produced. A chemiluminescent compound is added into the solution. Chemiluminescent compounds are substances that emit excess energy as a photon, but excitation occurs as a result of reaction. Okay, how do I say that in human English terms? Fluorometry versus chemiluminescence. They are both based on the same principle of I'm exciting something all the way up here, and then when I hit the emission state there, I lose all of the energy, right? They're based on that same principle. So we have our absorption versus our emission, or our excitation. That's not how to spell that word. Our absorbance versus our excitation versus our emission. We are measuring in fluorometry the emission stage. In chemiluminescence, we are measuring the excitation stage, the production of that photon. We are measuring the energy of the initial reaction. We are measuring that moment of absorbance / excitation. A couple of examples of chemiluminescent compounds include luminol, acridinium ester, and dioxetanes. And we do use a photomultiplier tube in this, like we do in fluorometry, for the same reason. Listen to me, because this is a question you will be asked. Which is the most sensitive method? Chemiluminescence. Chemiluminescence is the most sensitive method. The reason chemiluminescence is the most sensitive method is because, like fluorometry, you're using a photomultiplier tube. You can measure very, very small amounts. You're measuring it on a blank zero background, okay? The difference is, in that process of going from absorbance and excitation to emission, you have the chance of, in fluorometry, losing that small amount of energy to the system and not being able to measure it, right? And so that comes through stuff like the self-absorbance, the self-everything else that we talked about, the issues with fluorometry. With chemiluminescence, because we are measuring this top level and we're not measuring that bottom level, we don't have to worry about that loss of energy as much via other methods. So there is less chance of energy loss, which means because there's less chance of energy loss, because there is no like self-quenching, self-absorption, or any of that, this maintains the sensitivity that would otherwise elevate the minimum amount of reaction occurring for us to be able to see what's going on. Most sensitive. Thank you. Okay. Now, chemiluminescence, again, most sensitive method. You don't have to care about self-quenching. It's also a pretty easy method. It's very straightforward. It's a very simple instrument. The instrument looks almost exactly like a spectrophotometer, but it has a photomultiplier tube instead of that basic photocell that we were talking about at the beginning. Disadvantages of it, though. We're sensitive crybaby. You put anything that interferes with that background, with that zeroed out black background into this system, you get any sort of light contamination, you get any sort of energy contamination, it's going to decrease the sensitivity and specificity of this instrument, which is not fun. Anyways, that's all, and you are now experts in spectrophotometry. Please message me if you have any questions, okay? Thank you.